Hi everyone, we are Team 4. I'm Zhao Fengfeng, the hardware leader.
I'm Ming Huang, the software lead.
And I'm Bing, the system integration and documentation lead. Together, we develop solutions for common campus frustration.
So we all have been there, walking into like 500-seat lecture hall, 5 minutes late, and you wondering how to find one empty seat while the professor is already talking. It's disrupted, inefficient, and stressful.
That's why our project, the Lecture Hall Seat Finder System, solves this by providing real-time occupancy data displayed right outside the hall doors.
To ensure our system was reliable, we developed a strict testing protocol. We focus on 3 phases: individual sensor calibrations, multi-sensors row stabilities, and wireless latencies.
First, we test force-sensitive resistor under different loads. We need to know if the sensor could tell the difference between a heavy backpack and a student.
During software testing, we monitored raw analog values. We discovered clear empty state at near 4095 and an occupied state below 3900. This data allowed us to set a firm threshold to our logic.
Then we move to row testing. We simulate a 4-seat row to ensure the SP32 could handle multiple inputs without dropping data packet during wireless transmissions.
Our final design is distributed wireless network. It starts as a seat where an FSR is installed under the cushion in a voltage divider circuit.
The brains of each row is an ESP32 microcontroller. It reads the analog signal and applies our logic. If the value is 3900 or less, the seat is marked as occupied. It then sends a binary string like 1010 via Wi-Fi.
These strings are caught by a central Arduino Uno R4 Wi-Fi. The Arduino aggregates the data from every row and then pushes to a display board located outside the classroom.
The display is a simple red and green grid. Green means go to find your seat, and red means keep moving. It is instant and intuitive.
We chose this specific FSR-based design because the data proved its accuracy. Our tests showed a massive buffer zone between an empty seat and an occupied one, which means almost zero false positives.
The system also means all our designs constrained. It is low cost, it uses minimal wiring due to the wireless ESP32 unit, and most importantly, it's scalable. Yeah, you can add 50 rows just as easily as you can add 1 or 2.
By offloading the processing to local row controllers, we keep the central Arduino from being overwhelmed, ensuring the real-time update requirement is always met.
Of course, no prototype is perfect. Currently, our FSR are sensitive to placement. If a student sits on the very edge of the seat, the sensor might not trigger.
To address this, future iterations could use a multi-sensor mesh per seat or a weight averaging algorithm to increase sensitivity.
We also plan to develop a mobile app so students can check seat availability before they even reach the building.
The seat finder system is a simple solution to a big problem, making produced lecture halls smarter and more efficient. Boiler up. This is an overview of our prototype. It uses an Arduino R4 Wi-Fi Uno from our Engineering 132 class, and also an ESP32U. So the idea of the prototype is to wirelessly, as you can see here, there's no wire to connect the Uno to the ESP32. So there's the sensor here. This is the FSR sensor, which detects force. So when somebody's sit on the seat, the screen's gonna detect it. As you can see here, when the value goes below the threshold of 3900, the seat is taken. And when I take my finger out, which cancels the force, the seat becomes empty. So we use a Wi-Fi connection from our phone hotspot. We connect the ESP32 to the hotspot and also the Uno R4 Wi-Fi. And the ESP32 is gonna send signal to the Uno R4 Wi-Fi through that personal hotspot and show the results here on this screen. We are on our way to further develop our prototype to a more extensive display, and also furtherly build our seats to 2 rows with 2 seats each. Thank you.